alcohols and phenols. We have seen that when in hydrocarbon, one hydrogen is replaced with the OH group, hydroxyl group, we get alcohols. When in aromatic compound, if one hydrogen is replaced, one or more hydrogens are replaced by hydroxyl group, we get phenols. Ethers are obtained by replacing hydrogen with the alkoxy or phenoxy group. So we can have aromatic ethers as well as we can have the aliphatic ethers. At the same time, my dear students, we have studied their nomenclatures. We have studied about the various types of or the classification. We have seen that monohydric, dihydric, trihydric, tetrahydric or polyhydric alcohols and phenols. We have studied about the primary, secondary and tertiary alcohols and primary, secondary and tertiary phenols. We have studied about the allylic alcohols. We have studied about the benzylic alcohols. And then we have studied about the phenols. We have studied their nomenclatures. As you can see that we have studied that we can have the alcohols which are having a compound containing CsP2OH. We have studied alcohols where they contain the compound containing CsP3OH. We have studied about the various names like phenol, orthocasol, metacresol, paracresol. We have studied about the hydroquinone. We have studied about the catechol. We have studied about the types of ethers like simple and symmetrical ethers or mixed and unsymmetrical ethers. We have seen their various nomenclatures and we have classified them into the primary, secondary, tertiary, allylic or benzylic alcohols and phenols. We have seen their nomenclature in detail. And now, my dear students, we are going to study in detail about the structures of various functional groups that we want to study. So, let us start the class after revision with the structure of the functional group. First, my dear students, let us have a look to this alcohol. So here we have the structure of methanol. You can see that this is what it is, the structure of methanol. In methanol, the carbon undergoes the sp3 hybridization. It combines with oxygen and that oxygen is bonded with hydrogen. The bond angle of COH is 108.9 degree. The bond length OH is 96 picometer, whereas the bond length CO is 142 picometer. This is how, my dear students, we understand about the structure of the alcohol functional group into methanol. Now let us have a look to the phenol, my dear students. You can see that in phenol we have all the carbon present into the aromatic ring, they are sp2 hybridized. This sp2 hybridized carbon combines with oxygen. So in phenol we have sp2co bond. This sp2co bond has a double bond character because this green colored dots which represents the uh, lone pair of electrons, these lone pair of electrons are involved into the resonance. So this electron involved inside the aromatic ring, and this is how this bond turns out to be double bond. If we draw the 5 various resonance structures for phenol, we find out that this electron ring or this bond in 3 resonance structures, these bond become double bond, and that is why this sp2co bond has a double bond character, and that is why this bond length CO is 136 picometer. You have seen that generally the CO bond length is 142 picometer, but due to this double bond character in phenol, the CO bond length is 136 picometer and the bond angle COH is 109 degree, my dear students. Same way when we look at the ether, my dear students, you can see that here in this ether, this is your methoxymethane. In this ether, you can see that there is again a C bond, O bond C. Again, this CO bond is 141 picometer, which is very similar to the 142 picometer that you can see into the alcohol. The bond angle is 111.7 degree. And here you can see that sp3CO bond. And that is why the bond length is approximately 142 or 141 picometer. So my dear students, if we compare the bond angle, we find that in alcohol, ether and phenol, we find that in alcohol the bond angle is 108.9 degree, in phenol it is 109 degree, whereas in ether it is 111.7 degree. That is why we can say that the bond angle is highest into the ethers, whereas the bond angle is lowest into the alcohols or smallest into the alcohol. The bond angle in ether is greater than 109 degree 28 minutes, whereas the bond angle in alcohols and phenols are almost similar to the 109 degree 28 minutes. When we look at the carbon-oxygen bond length, my dear students, in alcohol the bond length is maximum, that is 142 picometer. In ether the bond length is 141 picometer, whereas in phenol this bond length is 136 picometer. This is due to the double bond character of the CO bond present into the phenols due to the resonance effect. Now, my dear students, we are going to study about the preparation of alcohols. So let us study in detail about the preparations of alcohol. First, we shall study the preparation of alcohols from alkene. So alcohols can be prepared from alkene by the acid catalyzed hydration. Hydration is generally the process of addition of water into the alcohols. So alkenes can react with water. These alkenes can react with water, my dear students, in the presence of acid as a catalyst to form alcohol. Let us see this reaction. But before we see the reaction, let me read a note for you. In case of unsymmetrical alkenes, the addition reaction takes place in accordance with the Markovnikov rule. So you need to understand the addition. You need to understand that the addition takes place according to the Markovnikov rule. Now let us look at the addition of water into the alkene. See, alkene is represented with the help of the C double bond C. So this is your alkene molecule in which water molecule is added in the presence of H plus. H plus represents the acid catalyst. So when H plus is added, this H2O turns out into HNOH, and this HNOH is added in the form of, so water is added in the form of HNOH, and this is how we get the final product. Now, my dear students, let us understand the same reaction with one example. This example is of 1-propene. You can see I have shown you this 1-propene present over here. This 1-propene CH3CH double bond CH2 is added water. When we add water into the 1-propene, we get 2-propanol. Apart from 2-propanol, my dear students, we may get 1-propanol. But 1-propanol will be obtained only when there is a presence of hydrogen peroxide or some other peroxide. But according to the Markovnikov rule, the negative part of water, that is OH minus, would be added to the carbon, which is most substituted. What is the meaning of most substituted? The meaning of most substituted means the carbon should be bonded to the least number of hydrogen and maximum number of carbon. Here you can see that the second carbon is bonded with two other carbons, and that is why the second carbon is the most substituted carbon. And this is how we can get 2-propanol, because the negative part of water is being added to the second carbon and we get 2-propanol. This product is known as the Markovnikov product. This problem of whether we are going to get Markovnikov product or anti-Markovnikov product does not arise into the symmetric alkenes. So let us understand the same with the example of symmetric alkene, my dear students. Here you have the symmetric alkenes. This symmetric alkene is the ethene. You can see here, my dear students, that around the double bond, both the sides are same. So if you put a mirror here, the half part of the molecule becomes the mirror image of the another half part of the molecule. This is how water, when we add water into the ethene, we get ethanol. Now OH, this OH, if it is bonded to the first carbon, or OH if it is bonded to the second carbon, the product whatever it is obtained is known as ethanol itself. So my dear students, when there is symmetric alkane, you can see here, I have even mentioned that when there is symmetric alkane, we need not to worry about the product whether it is Markovnikov product or anti-Markovnikov product. But when we have the unsymmetric alkane, my dear students, we should think about the product, whether it is the Markovnikov product or anti-Markovnikov product. Anti-Markovnikov product is not obtained in case of the acid catalyst hydration. In acid catalyst hydration, my dear students, as the peroxides are not present, we are going to get the Markovnikov product. This is how, my dear students, we understand the acid catalyzed hydration. Now, my dear students, a very important point about this acid catalyzed hydration that we are going to study, it is known as the mechanism. When we study the mechanism of the acid catalyzed hydration, we realize that this acid catalyzed hydration, my dear students, takes place in 3 steps. You can see here on your screen, we have step 1, we have step 2, and we have step 3. So let us understand this mechanism in 3 steps, one by one. Let us look at the mechanism in 3 steps, one by one. Here we are going to study the mechanism of the acid catalyzed hydration of alkene. In the acid catalyzed hydration of alkene, my dear students, in the first step, protonation of alkene to form carbocation by electrophilic attack. H2O in the acidic medium turns to be H3O plus. So first you can see that here we have H2O. In oxygen we have 2 lone pairs. This lone pairs attacks on H plus. So this positive charge goes on the oxygen and that is how we get H3O plus ion. You can see here I have shown you the structure of the H3O plus ion. Now this H3O plus ion reacts with alkene. You can see here we have alkene. This alkene is represented with the double bond. This double bond has got more electron. This electron of double bond attacks on the hydrogen of hydronium ion H3O plus. So this bond, where we have shown the red color arrow, the electron involved in this bond, they goes on oxygen and the hydrogen get combined with one of the carbon. The carbon with which hydrogen combines does not get any charge, but the other carbon where hydrogen does not combine, it gets the positive charge, and from hydronium ion we get water molecule where we have shown only 1 lone pair on the hydronium ion but 2 lone pair in water, because the bond which is broken takes the 2 electron with it, and that 2 electron combines, or that 2 electron we can represent into the water molecules. Now, my dear students, we have seen how the carbocation is formed and how the water molecule is formed. There is again an attack which is known as the nucleophilic attack of water on the carbocation. So when there is nucleophilic attack of carbocation, nucleophilic attack of water on carbocation, we get additive species. What happens? This extra electron which are present on oxygen, they attack the carbon which is having positive charge, and water itself as a molecule is added to the carbocation. And this is how we get an additive species which is having positive charge on oxygen. You can see that this oxygen loses its 2 electron to make an extra bond with this carbon. And that is why here we have shown 4 electrons, but here we have shown only 2 electrons. Then we have the third step, my dear students. This additive species, which is having the positive charge on oxygen. My dear students, you are aware that oxygen is more electronegative element, and that is why when there is a positive charge on oxygen, it is less stable. As this positive charge on oxygen is less stable, this OH bond is being broken, and the electron of this OH bond comes on oxygen. But at the same time, water molecules even attack on this oxygen. So in the third step, there is a deprotonation of species. This deprotonation takes place because the positive charge on oxygen is not stable, and that is why the deprotonation takes place. Deprotonation means removal of hydrogen. So as the hydrogen is removed, the water attacks on the hydrogen and again form hydronium ion H3O plus. As the electron from the OH bond comes on oxygen, we have shown 4 dots of electron or 2 lone pair. And this is how, my dear students, in the third and the final step, we get alcohol produced. The hydronium ion produced over here is used again back into the first step. You can see that here in the first step itself, my dear students, in the first step, we have used the hydronium ion. So this hydronium ion, which was produced in the third step, is utilized again back into the first step. You can see easily, my dear students, that when we take a case of the hydronium ion, you can see here we have formed the hydronium ion. This hydronium ion, whatever it is produced over here, this hydronium ion again utilized into this first step back. So this is how this hydronium ion is utilized into the first step back. So this is how, my dear students, the reaction keep going on and more number of molecules are converted into the alcohols from alkene. Now, my dear students, if you have not understood anything from this mechanism, you can ask me, or else we can move to the next part. My dear students, is there anything which you cannot understand from this mechanism? You can ask me, please.
No,
Do you have anything to ask, dear students?
no, sir.
Only one boy replies. All of you can tell me, do you want to ask anything?
No, sir. No.
No,
No,
sir.
sir.
Great.
No.
Have you understood everything? Please learn this mechanism, because this mechanism is frequently asked into the board exam, and it is very important that you learn all the mechanisms involved into our syllabus. So please keep learning this mechanism. Shall we move to the next part, my dear students? अगले टॉपिक पे
Yes,
चलें?
Yes.
Yes, sir.
चलिए
Yes, sir.
let's move to the next topic. We have seen that alcohols can be prepared by the acid catalyzed hydration. So apart from the acid catalyzed hydration, alcohol can also be prepared by a new method, another method, which is known as the hydroboration oxidation. So now, my dear students, let us study about the hydroboration oxidation reaction. In 11th standard, my dear students, we have studied about diborane. Diborane is B2H6, which can also be written as BH3 twice. Diborane B2H6 reacts with alkenes to give trialkyl borane as an addition product. This is oxidized to alcohol by hydrogen peroxide in the presence of aqueous sodium hydroxide. So please pay attention here, my dear students. Remember that we have propene, which is an unsymmetric alkene. Only unsymmetric alkene have a problem whether the product is going to be Markovnikov or anti-Markovnikov. This propene reacts with BH3 twice, which is known as the diborane. This hydrogen present into the BH3 is replaced by propene. When this hydrogen is replaced by propene, this propene combined with the BH2 as a propyl group. So you can see that CH3, CH2, CH2, BH2. So this is propyl diborane. That is how it takes place. This propyl diborane, by the displacement of another hydrogen with propene, become dipropyl diborane, or even it converts into the tripropyl diborane. This tripropyl diborane, in general, it is called trialkyl borane. Remember, my dear students, this trialkyl borane reacts with hydrogen peroxide. We are already aware that if there is a presence of hydrogen peroxide, we are going to get anti-Markovnikov product. So when this trialkyl borane reacts with hydrogen peroxide, H2O and alkali, this alkali NaOH produce OH minus. And thus, this trialkyl borane is simply converted into propane 1-ol. This trialkyl borane is simply converted into propane 1-ol, and my dear students, this propane 1-ol is nothing but your anti-Markovnikov product. Apart from this propane 1-ol, during the hydroboration oxidation, we get BOH thrice or H3BO3, which is a byproduct, which is also known as boric acid. So this is how, my dear students, we study about the hydroboration. While studying the exercise of the chapter 1, we have even studied about the hydroboration. The addition of borane to double bond takes place in such a manner that the boron atom gets attached to the sp2 carbon carrying greater number of hydrogen atoms. The alcohol so formed looks as if it has been formed by the addition of water to the alkene in a way opposite to the Markovnikov rule. In this reaction, alcohol is obtained in the excellent yield. So my dear students, when we perform or when we choose hydroboration oxidation, the product obtained is in a good amount, in a good percentage, and that is why we can say that by the process of hydroboration, the reaction alcohol is obtained in an excellent amount. Now, very important point about hydroboration. Hydroboration oxidation was first reported by H.C. Brown in 1959 for his studies on boron containing organic compound. Brown shared 1979 Nobel Prize in chemistry with G. Whitting. So, my dear students, for discovering the hydroboration oxidation, the scientists have got Nobel Prize too. I hope, my dear students, this was the revision of the hydroboration and you would have understood it. Still, if you have any doubt, you can ask, or we can move to the next process for the preparation of alcohol, which is known as the preparation of alcohol from carbonyl compounds. Do you have anything to ask?
No, sir.
Okay.
No, sir.
Okay, then let's move to the next.
No,
By the
sir.
reduction of aldehydes and ketones. We can get alcohols by the reduction of aldehydes and ketones. Aldehydes and ketones are reduced to the corresponding alcohols by addition of hydrogen in the presence of catalyst. This is what it is also known as the catalytic hydrogenation. Now, the usual catalyst is finely divided metal such as platinum, palladium or nickel. Aldehydes and ketones can be reduced by LiAlH4 or NaBH4. My dear students, this LiAlH4 is known as the lithium aluminium hydride and NaBH4 is known as the sodium borohydride. Aldehydes yield primary alcohol, whereas ketones yield secondary alcohol. Please remember, my dear students, that whenever the aldehyde is treated with hydrogen and an active metal, it produces primary alcohol. When a ketone is allowed to reduce with the help of any catalyst like sodium borohydride, it gives us the secondary alcohol. In other words, when reduced, aldehyde gives primary alcohol, ketones gives secondary alcohol. Let us study the same with some examples. We have propanol, that is your CH3, CH2, CHO. When it is reduced with the metal palladium in the presence of hydrogen, it gives 1-propanol. My dear students, this 1-propanol is a primary alcohol, and that is how we understand that aldehydes on reduction will give us the primary alcohol. Now, my dear students, we have 2-butanol. This 2-butanol is ketone. This ketone, when it is reduced with the sodium borohydride, it produces 2-butanol. You can see that the carbon with which OH group is bonded with 2 other carbon, and that is why 2-butanol is a secondary alcohol. My dear students, for your information, LiAlH4 is known as the lithium aluminium hydride and NaBH4 is known as the sodium borohydride. By the reduction of carboxylic acid and esters, we can also get alcohols. So we can prepare alcohols by the reduction of carboxylic acids and esters. Carboxylic acids are reduced to the primary alcohol in the excellent yield by lithium aluminium hydride, which is known as the LiAlH4, which is a strong reducing agent. Please remember, lithium aluminium hydride is a strong reducing agent. It is very expensive too. So you can see that we have represented carboxylic acid with the formula RCOOH, which is reduced by the LiAlH4 in the presence of water. We get alcohol RCH2OH, which is a primary alcohol. Let us study the same reaction with the example. If you take acetic acid and allow it to reduce with the help of the lithium aluminium hydride in the aqueous medium, we get ethanol. So instead of acetic acid, if you take propanoic acid, you will get 1-propanol. If you take butanoic acid, you will get 1-butanol. This is how it goes. Now, my dear students, we are going to study an important point. This important point we are going to study in the form of give reason. That we shall study tomorrow. Today, my dear students, let us revise whatever we have seen. Let us do a small revision for whatever we have studied today. My dear students, today we have started our class by studying the structure of the functional group. You might have seen that we have studied the structure of methanol, we have studied the structure of phenol, we have studied the structure of methoxymethane, where we have the bond angle for alcohol is less than phenol is less than ether, but the bond length alcohol is greater than ether is greater than phenol. The bond length smaller in phenol is due to the double bond character of CsP2O, whereas both in ether as well as in alcohol we have CsP3O. Then we started studying about the preparation of alcohol. We have studied the acid catalyzed hydration. In the acid catalyzed hydration, my dear students, we have seen that when we have unsymmetric alcohol, we get Markovnikov of product, and when we have symmetric alcohol, we need not to study about the product, whether it is Markovnikov of product or anti-Markovnikov of product. We have seen the mechanism of acid catalyzed hydration in three steps. In the first step, the alkene is converted into the carbocation. In the second step, carbocation combined with the water and give us the additive species. And in the third step, the additive species undergoes the deprotonation and give us alcohol and hydronium ion. This hydronium ion can be utilized again for the first step. Apart from the acid catalyzed hydrogen, alcohol can also be prepared by hydroboration oxidation. In the hydroboration oxidation, my dear students, the alkene reacts with diborane and turns out into the trialkyl borane. This trialkyl borane is allowed to react with hydrogen peroxide and water in the presence of alkali to give us anti-Markovnikov product and boric acid. Remember, my dear students, the scientist discovered the hydroboration reaction has got Nobel Prize. We can even get the alcohols by the reduction of the carbonyl compounds like aldehydes and ketones. Aldehydes and ketones can be converted into alcohol by the reduction. That reduction may be with the help of the metal and hydrogen, or by the reducing agent like sodium borohydride and lithium aluminum hydride. Aldehyde always gives primary alcohol and ketone gives secondary alcohol, my dear students. We can even prepare the alcohol from the carboxylic acids. So by the reduction of carboxylic acids and ester, we can get the alcohols. My dear students, if the carboxylic acid is allowed to react with lithium aluminum hydride, we get primary alcohol. We have seen the example of acetic acid, which is converted to ethanol. Same way, my dear students, propanoic acid will be converted to propanol, butanoic acid will be converted to butanol. Now, if you have any doubt, my dear students, you can ask me. Do you, dear students, do you have any doubt to ask? You can ask me. Hello.